Water, it's basically defines our planet, it powers our industries, and it sustains our very lives. For you as a future civil engineer, it's way more than just a resource. It's really the ultimate grand challenge, a super complex puzzle of scarcity, safety, and sustainability. I mean, just look at our planet from space, right? It's this beautiful world of blue, water covers something like 70% of the surface, which it really creates this illusion that it's just endless, that we've got more than we could ever need. But here's the thing, that picture can be a little misleading.
Because this is the number that really changes everything. Just 2.5%. That's it. That's all the fresh water on planet Earth. And get this, what's even crazier? Only a tiny fraction of that is actually accessible for us to use. This one little number is exactly why your job as an engineer is so incredibly important.
So that really brings us to the heart of the problem, what we call the grand challenge for civil engineering. How in the world do we manage this absolutely essential, but very finite, resource when demand just keeps growing? It's this huge paradox, and honestly, you, as engineers, are the ones who are going to have to solve it. And believe me, the stakes could not be higher. Water is the foundation of all life. It's the engine that drives our economy, from factories to farms, and it's our #1 defense against diseases. So when you think about your job, you're not just managing some liquid. You are literally protecting the pillars of our entire society.
Okay, so we've got this massive challenge. What do we do? How do we even begin to respond? Well, we do what we do best. We engineer a solution. We build an entire system that's designed to take on nature's paradox and deliver this precious resource to people safely and reliably. And that solution, that incredible feat of engineering, is the water supply system. You can think of it as this really complex web of pipes, pumps, and plants. And it all has one clear goal: get safe, clean water from wherever it starts, all the way to a consumer's tap, ready to go and with enough pressure to work. And this image gives you a great snapshot of that whole journey. I mean, look at it. It starts way out in the watershed, gets collected behind a dam, travels through these huge pipes to a treatment plant, then it's pumped up to a storage reservoir, and then it flows through a massive distribution network right to our homes. It is just a massive, incredibly interconnected system from start to finish. Now that looks super complex, right? But to make sense of it all, we can actually break it down into 5 key pillars, or stages. First, you have to manage and protect the source. Then, you treat the water to make it safe to drink. After that, you store it so you have enough for peak times. Then, you distribute it. And finally, you have to manage how much people are using and control any losses from things like leaks. Every single one of these is a critical field you'll need to master. And no matter what you're doing, whether you're managing the source or fixing a leak, every single decision you make comes down to these 3 core objectives. The water has to be safe, it has to be sufficient to meet everyone's needs, and the whole system has to be sustainable, so we're not damaging our water sources for the future. Safe, sufficient, and sustainable. That's the mantra. Okay, so we know the water needs to be sufficient and sustainable. But before you can even think about designing a system, you've got to ask a fundamental question. Who actually needs the water, and what are they using it for? This is where we get into the science of mapping water demand. Generally speaking, we can split all that demand into 2 big buckets. You've got domestic use, that's the water for our daily lives, drinking, cooking, showering. Then you have industrial use, which is often for things like processing and cooling, and it uses a massive volume of water. And trust me, designing for a neighborhood is a whole different ballgame than designing for a factory. So let's dig into that domestic use for a second. You might think most of it is for drinking, right? But take a look at this. About 28% is for watering lawns and gardens, 17% for toilets, 16% for showers. As an engineer, knowing that over half of the water is literally going down the drain or onto the lawn, that is absolutely critical for designing effective ways to save water. All right, let's zoom out from the household and look at the whole picture. So you have your domestic and commercial use, you have industrial use, and places like schools and hospitals. But the big one, the elephant in the room, is agriculture. It is by far the largest consumer of water on the planet, and its demand can be super seasonal, which creates a huge headache for planning. So we've talked a lot about quantity, how much water we need. But what about the quality of that water? As an engineer, you have to be an expert on the physical and chemical properties of water. And this isn't just some boring chemistry lesson. These are the real practical things you'll be measuring and controlling every single day on the job. So let me ask you a question to get us started. Imagine you have two glasses of water. One of them looks a little cloudy, and the other one tastes kind of salty. From an engineer's perspective, what is the real difference between these two problems?
Well, the answer all comes down to one key concept: suspended versus dissolved solids. See that cloudiness? We call that turbidity. It's caused by tiny particles just floating around in the water, kind of like dust floating in a sunbeam. Now that salty taste, that's from what we call total dissolved solids, or TDS. These are things that have completely dissolved into the water. You can't see them at all, just like when sugar vanishes in your tea. And for both, there are strict limits you have to hit.
All right, another big one you absolutely have to know is pH. You've probably seen this scale before, right? It measures acidity and alkalinity. For us in water supply, we are always aiming for this sweet spot, a really narrow range between 6.5 and 8.5. Why? Because if the water gets too acidic, it can actually eat away at the pipes. And if it's too alkaline, it can mess up our treatment processes. It's this constant balancing act you have to manage. And pH is just the beginning. Think of it like a dashboard with a bunch of key indicators you're constantly monitoring. You've got to watch chlorides for taste and corrosion. You're managing hardness to stop pipes from getting clogged up with scale. And you even have to measure dissolved oxygen, which tells you how healthy the source water is. You need at least 5 milligrams per liter just for fish to survive. And the reason we have to be so obsessed with these parameters is because our water sources, the very start of the whole system, are constantly under threat. Defending them from all kinds of contamination is one of your most important jobs. And the threats you're facing really depend on where you're getting your water from. With surface water, like from rivers and lakes, it's right out in the open. It's exposed to things like runoff from cities and farms. But groundwater? That's a different story. The threats there are invisible, creeping in from below, like a leaking underground fuel tank or nasty stuff seeping out of a landfill. So what you end up with are two totally different kinds of pollution problems. Surface water, it gets polluted fast and you can usually see it happen. But groundwater pollution, man, it's sneaky, it's insidious. The pollutants seep in really slowly, they can stay hidden down there for decades, and once an aquifer is contaminated, it is incredibly difficult and expensive to clean up. So when you put it all together, the scarcity, the complex systems, the chemistry, all these threats, it all points to one thing: the engineer's mission. This is what defines your job. It's about securing the future of the most important resource we have. And this quote right here, it just perfectly sums up what this is all about. This isn't just about building bigger pipes or more powerful pumps. It's about smart, effective management and being relentless about pollution control. Both are absolutely essential to protect a resource that, once it's really messed up, is nearly impossible to get back. So I want to leave you with this question, because this is the challenge that's going to define your entire career. Our population is growing, demand is rising, and the stress on our limited water resources is getting more intense every single year. Tomorrow's problems are going to need brand new ideas and new solutions. The real question is, what are you going to do? How will you engineer the future of water?